Hello, and today we're doing another lab video. This one is going to be on the vapor pressure by boiling point method. That's number 5 in your lab calendar, right? And well, what we're after, right? So this time we can actually see the screen. We'll see here that relationship, right? dlnp over p naught, d1 over t. A plot of the log of the equilibrium vapor pressure divided by the standard state pressure versus 1 over t should be a straight line and allow us to determine the enthalpy of vaporization. And that's what we're after today. We want to somehow measure the equilibrium vapor pressure, right, of 2 different liquids, ethanol and N-heptane. And so how are we going to do that? Well, we need some apparatus for that. Proper safety equipment, as always, right? And we're going to need a vapor pressure apparatus. MicroLab box. Oh, the MicroLab box is up. There's Mr. MicroLab box. We're going to use that today to measure temperature and pressure. And also time, though we don't need to record that, actually. Heating mantle. We've got a heating mantle down here. So heating mantle. The variac back here, so we can control the power into the heating end. Boiling chips, right? Those we keep in the flammables cabinet because they're flammable. The boiling chips are inorganic, so they're over here alphabetically under B for boiling, right? So stick those chips in. Right? Good. So we got all of that stuff. What else do we need? We need samples. We got the samples, and we need to put this all together. So how we're going to do? All right. So you probably have used a distillation apparatus before, and this is a distillation apparatus, right? That we've got round bottom flask here. Got a 2-prong round bottom flask. We got the heating mantle down there. Heating mantle is hooked up to the variac, so we can control the power. Then now we've got a condenser here. Got water that's going to come in from the bottom, go out through the top. Important that it goes in through the bottom, out through the top, so that you really get nice flow up through there. Okay. So that much you've probably used before, and you probably had that opened at the top when you did it in organic. But now instead, we have a valve up here, okay, so that we can connect this to, we've got a ballast jar here, right? We've got a vent valve, another valve here. And then we've got the pressure apparatus going back to the MicroLab box. And over here, we've got another valve. There, we can see the valve there with the black top on it, right? There we go, there's the valve. Oh, there it is. Okay, going over to our pump. Got a mechanical pump back here, right? Turn that on, make some noise. All right, so right now, let's, why do we need the vacuum? Well, because what we want to do is just measure the pressure. We're going to get rid of the atmosphere above our sample. We want it just to be the ethanol or heptane that's in there, so that we can measure the pressure and control the pressure in that region, right? All right, so we attach our round bottom flask. We get the little connector on there so it doesn't fall off. I'm going to cinch this puppy up here and get that nice and tight on the bottom there, right? So that we've got the heating mantle in contact with the round bottom flask, and we have a thermistor has been jammed through a rubber stopper so that this makes a nice vacuum seal contact as well. Stick that in here so that all of that should make vacuum. Now, 2 different kinds of valves. We want to understand these 2 valves. This one, you've probably seen valves like this before. This is a simple stopcock that we've got in here. When it's in line parallel with the tube, it's open. When it crosses it, it's closed. When it crosses it, now this is the vent valve. Okay, this is where we can vent the system back up to atmosphere. We can add pressure that way, right? The other valve, the one that's back here, right? That one is much different. This one you'll see has more of a black rotary cap to it. and it experiences backlash. It's been closed now, right? All right, that's been closed. When we want to go open it, we try to turn it counterclockwise. And at first, it just feels really loose and nothing's happening. That's the backlash. When we change the direction that it was rotated, at first it does nothing. And then you'll feel it, it's catching, and wait for it. There you go. You can hear the pump. When the pump is under load, you can hear its sound change, so you know when it's pumping. But we don't want to open this too far. If you keep unscrewing this, boom, the whole valve stem will come out. And it's supposed to do that, so we can clean it. But we don't want to get it that far out in the leak, right? So we open that a bit. You can hear that everything's pumping down. Sounds good, right? We're pumping down the ballast. The ballast is here to provide a bigger volume to the system. It provides a cushion and a time constant so that the pressure doesn't jump up and down too much with changes that are going on in our system, all right? We also have another valve up here on top of the condenser. Very important to control this one the same way as that one. When it's in line, it's open. When it's perpendicular to the tube, it's closed, all right? So right now, that's closed, so we're not pumping this, we're pumping the ballast valve. What's the pressure? Well, the way we can figure out what the pressure is to start up MicroLab. So we're gonna click on the MicroLab icon there. We'll start up the MicroLab box. And we're going to start a MicroLab experiment. And we're gonna add sensor. We're gonna add a pressure sensor. All right, pressure, grab that there. Choose factory units of kilopascal. And we're gonna put the pressure on the axis over here. We got pressure here, we got pressure there. 3 figures, I doubt it, right? Let's edit this display and make that 2 digits over there. So we've got more significant digits and they're bouncing around, right? Okay. We also want to add a temperature sensor. We got the temperature sensor. It's plugged into A. That's going to be the thermistor plugged into A. We're going to use the factory calibration. We're going to drag the thermistor over to the axis over here. We got the value down there. Again, let's edit that display so that we only have 2 digits there so it's not bouncing around all over the place. Good. So we got temperature and pressure, but oh, wait a second. We're going to add one more. We're going to add a timer, and then we will put that, the time, on the x-axis, and then we can watch how pressure and temperature change as a function of time. We don't actually need time down here, so we can just remove that. Right-click on it and remove it from the display down there. Okay, so right now we've got this thing. It's pumped down out here, the ballast region. Okay, all of this down to 0.68, and if I open up the valve up here, wham, okay, I open this part out, it gets pumped out now, right, pressure went up. If we want to check for a leak, right, what we can do is check for a leak. We can put that valve to the pump, close it off. Again, I experienced that backlash, right, that when I first start to turn it up and up and happens, and then you feel it catch. And then you close that all the way down, boom, and it stops. And then we take a look at the pressure here. The pressure is not shooting up. Good, the pressure is not shooting up. We don't have any leaks in here. Excellent, okay? So now what we want to do is we confirm that our vacuum system is actually a vacuum system. Now to put the sample in, we need to take the flask off, right? But we can't take the flask off now because, don't forget, the atmosphere is pushing on that, right? And so it's being held together by the vacuum in there. So what we need to do first is vent the system up. Oh yeah, we can hear that, right? We've got this valve closed. Everything is open to the pressure gauge, to that region in there. So we open up the vent valve and sure enough, the pressure is rising again up to 100 kilopascals. Then we can remove this. We have to loosen back here, right? We can now take the thermistor off of there, snap that off, and we can remove the round bottom flask. All right, so what are we gonna do? If you look in the procedure, it tells us to put about 50 mLs of our liquid. Oh, okay, so I've got 50 mLs. This is the cooking show part where my assistant, i.e. me, before I started filming this, has already filled up 50 mLs of ethanol, and we can pour that into our flask. And it doesn't have to be exact, so I've just, poured it in there roughly. Boom. All right, we get that in there, good. And then we want to provide nucleation sites, right, for the boiling, make the boiling easier. So we're going to put a couple of boiling chips in. Now, got to be careful. The boiling chips, right? Boiling chips are kind of powdery, right? You only need a couple. And they're kind of powdery because they're all banging against each other. And when we stick them in here, we want it to go straight down the center. Okay? We don't want to get any dust on the joint up here. Why not? There is vacuum grease on there, right? We need to make that seal up here. We put a very thin layer. And when I say a thin layer, I mean we get our tube of vacuum grease, take a little applicator stick, i.e. a big Q-tip, like, one of those swabs that they need to jam up your nose for a coronavirus test. Yeah, one of those guys. We got them all over the place, right? Okay, so, hot item right now. So what you do is you take just a very tiny little bit, and you only need a thin film, very thin film. It shouldn't glom on there, right? It's just a thin film of vacuum grease that you need to make that seal, right? But the vacuum grease is sticky, right? It's great at making a seal, but it can also get some of that dust stuck on there. And we don't want any of that dust sticking on there, right? Because if the dust sticks on there, it will stop the vacuum seal. We already tested everything. We know we don't have a leak, but we could cause a leak if we accidentally get dust on there. All right, so we got some boiling chips in there. Got this. We'll put it back together. Right. Wedge it in, just a little bit of vacuum grease, thin film of vacuum grease up there. All right. We're going to cinch this back up to make good thermal contact with the heating coil. Our temperature probe, the thermistor, we've got to stick in here. Now, we jam that in there, we get a good seal, and then there's something very important. But now we look in here and we take a look at where the temperature probe is, and it should be up here in the vapor phase. It's the temperature of the vapor that we want to measure, not the liquid. So just take a look and make sure that the thermistor has not gone all the way down into the liquid, right? We don't want to know about the temperature of liquid. We want to have the vapor condensing onto the temperature probe, and we're measuring that temperature, right? Okay, so now everything has been vented again. Let's close this up. We've got atmosphere in here. We've got atmosphere in the ballast valve as well. Got this closed. We're measuring the pressure. So we can open up this. Backflash, backflash, backflash. You catch it. Boom, you can hear the pump under. Load again. Always good to know what's going on. Take a look at the pressure. Pressure's coming down nicely, right, as it drops down now below 10 kilopascal. Now, we don't have to get all the way back down to zero pressure, okay? What we want to do is, one, get this down to like 7 to 10 kilopascal. So we're gonna open this valve up here, right? We're gonna open up this valve, and we're gonna let the atmosphere rush out of here. But we got our liquid in here, right? We don't want to open this up too fast, because we open this up really fast, whoosh, we can get a big splash of stuff into the condenser and maybe into the ballast valve. We don't want that to happen. So we're going to open this slowly up here, and that will let, once that's open, that will let the gas start to come out of this region, right? And you can start to hear some, right? And as the pressure drops, you can see, oh, it's starting to boil in there as the pressure is dropping down, right? Okay, so we'll close that off and let it settle down a little bit. Let the pressure settle. open this up again slowly so we don't get a big rush up out of there. We're getting dissolved gases out of here. We're getting the atmosphere out of there. We're trying to get this to be filled with just the vapor of our sample, which is the liquid. We don't want the boiling to be too violent so that it doesn't go shooting off up through the top there. Okay, so now pressure's pretty low. I think we'll close this off. And let's take a look. We want this to sort of stabilize around 7 to 10, something like that. We've got this all the way open. And now the pressure is slowly coming up. It's still bubbling around a bit, right? Not so regularly now, as it's trying to equilibrate to about room temperature, right? Okay, so that's good, right? And we could even, right? We could even start this here, and then we would see pressure is in red, temperature is in blue, how those are changing, right? But if we pump a little, pressure's going to drop. It'll start bubbling again. If I close that off, oh, the pressure goes up. Temperature doesn't respond as quickly, right? But the pressure certainly responds to whether I have that pumper going or not. I don't need the pump anymore, or at least I don't need it right now. I'll need it again later, but I don't need it anymore. So I've got this closed. Make sure you're going to turn the pump off. Always close that valve first, right? This valve going to the pump is closed, then I can turn it off. The reason why you have to close that valve first is if you close this off and have that open, you might get an inrush of oily gases out of the pump. You don't want that to happen. So you always close the valve first, then you can turn off the pump. Okay, so now what we want to do is start heating the heating manual, run some liquid through here, turn that on there, boom. Okay, water coming in the bottom, going up through the top, coming out there. We've got that running. We want to adjust the pressure to 20 kilopascal. Then we're going to start heating it until it's boiling steadily. Right? We can adjust the pressure by allowing a little bit of gas in through here. This is the vent valve again. Right? The easy one, no backlash on this one. Let some gas in, get it to about 20 kilopascal. So a little bit lower than that, right? And then what we're going to do is we turn on the variac, heat it up to about 20, 25, actually probably a little bit higher. And then what we want to do is start boiling. Oh, wait a second, did something terrible. Got to be careful, right? When you normally do, didn't do something terrible, but I could have done something terrible. I want you to be aware of this, right? That when you normally do a distillation, very often when you've done a distillation, you have this open, right? Right now it is open to the ballast and all of that. That's fine, okay? If it's open to the atmosphere, you don't have any trouble with getting too much pressure in here. If you have this closed, right, perpendicular to the tube, if you have it closed and you start to heat down here, you can build up pressure as you start to boil that off. Don't let that happen. Make sure that this is open before you turn this on. It was open before I turned that on, but I want to point that out. You could get an explosive pressure buildup if you have this valve closed and you start heating. So we've got that open. The pressure is okay. We turn this, crank that up. Now what we're going to do is allow the gas to equilibrate. We'll get a nice rolling boil going, and then we're going to measure the temperature and pressure when the system has equilibrium, okay? So we have to wait about 15 minutes for the first one to happen because we got to get all of this to warm up. We got to get everything equilibrate to temperature, right? What we're going to do is we heat up the system and set the pressure around 20 kilopascals, a little bit higher to start off with. Then we're going to let the system equilibrate. We'll know when the temperature and pressure are stable that it will equilibrate. Then we'll let in a little bit more gas, pump up the pressure. We want to get the system to boil again. Oh, wait a second. If the pressure is higher in the system, you're going to need to add heat to it to get it to boil again. Ah, right. So when we increase the pressure, we also need to increase the heat. That is, we'll have to turn up the variac, right, to get the system to boil again. Once we get a steady boil, we wait until the temperature and pressure equilibrate, measure the temperature and pressure, and then so on until we get to our maximum temperature or maximum pressure. What's the maximum pressure? This is a vacuum system. It wants to be at atmospheric pressure or below. We don't go above atmosphere. Don't want to go much above, 100 kilopascal. Because if we get above 100 kilopascal, poof, you can just start to blow things off of here, right? We're not going to do that. So we don't go much above 100 kilopascal. We can get to 100 kilopascal, don't go above it, right? Because it's a vacuum chamber, but atmospheric pressure and below, we don't want to go above 100 kilopascal, so nothing blows up, right? We try to avoid blowing things up, right? If you're going to blow anything up, go to organic lab. So go ahead and blow things up there. Not here, right? Don't tell them I sent you. All right. Now, what is our data going to look like? Oh, guess what? I have some sample data here. This is like a little staircase to heaven, right? There you go, staircase to data. Maybe not heaven, but at least to data. And so what we have here is, right, the red is the pressure, the blue is the temperature, right? We set the pressure by adjusting the vent valve, allow the system to equilibrate, turn up the heat until we get a steady boil, and then eventually we'll get a nice steady temperature. Boom, we measure the temperature. And we do this in about 10 kilopascal steps. And so we go all the way up till we get to around 100 kilopascals, a little bit higher, but not too high because we don't want this system to go supercritical on us, right? We don't want to go much above atmospheric pressure. All right, so there we go. We've controlled the pressure, right, with the pump or letting gas in through the vent valve. We know how to control those valves, the two different types of valves we have, one without backlash, one with backlash, right? We know we've got a thin film of vacuum grease on there to make it seal, but we got to keep that clean. You don't get the dust in, we got to be careful about that. Get the system to equilibrate without blowing everything up through the top here. We have this valve open whenever this is hot so that we don't build up pressure there. We don't crank the pressure down and open that up very quickly to shoot stuff out the top there, and we don't over-pressurize the system. Now, what about the data, right? Oh, wait a second. So we said, tying this back to our PCAM lectures, right? We said, right, a plot of ln pressure, what we just measured, divided by the standard state pressure, 100 kilopascal, versus 1 over t, the slope of that, right? This is derivative of the slope. That should be delta H over R minus delta H over R, right? So if we take the slope times minus R, we should get delta H of vaporization for this system. All right, so what does that mean? Again, let's help you with the data analysis here. So we're gonna have a plot, right? We measured the pressure in this system. We divide through by the standard pressure. Standard pressure, right, is just 100 kilopascals, right? And then we're going to take the log of that. Natural log, here would be not, we plot that versus 1 over t. And of course, we're doing that in Kelvin. The data came in Celsius. We got to convert that to Kelvin. 1 over that. And what you're going to get is some of the finest data you've ever taken. This one really works well. You're going to get a nice straight line, right? We fit that to a line, and what we know is that minus r times the slope, right, is equal to delta H. We're going to call that our experimental value of delta H, right? Good. You get one of those for ethanol, get one of those for N-heptane. Now, what we want to do, as always, is not only report that, we want to report the slope or the uncertainty. Oh, the uncertainty comes from the uncertainty of the slope, right? And so if we have the uncertainty in the slope, to get the uncertainty in delta H, we're going to have to multiply by R. So make sure you have an error analysis section that explains that you took the slope in Igor, you found the uncertainty in Igor, and then you have to multiply by R to get the uncertainty in delta H. Good. Then you go and you look up a value of the enthalpy of vaporization in the NIST book, right? And you compare these two and you say, wow, this data was so good. Wait a second, why don't these two numbers agree? Well, one reason is we know now that the enthalpy, right, delta H, enthalpy change, is a function of temperature. And so, yes, it's linear over a small range, but actually there's a larger curve here that really does change the shape a little bit. And so we've measured it over a certain temperature range, and that's where our value pertains to, right? We have an upper temperature, we have a lower temperature. This is 1/2. And the place that our data is most appropriate for is right in the middle of this, right? So we have T experimental, it is in the middle. It's the average of the high temperature and the low temperature, okay? So our experimental value pertains to T experimental, but the one we looked up in the NIST web book, it's probably taken at some different temperature. And now what we should do is correct this to the same temperature so that we can compare apples to apples. We compare delta H vaporization from the literature at the temperature of our experiment to the value that we took at this temperature. All right, how do we do that? How we do that, of course, we now know because we've done this in PChem lecture as well, right? And that is that we have this correction factor right there, right? Okay, so delta H evaporization at some arbitrary temperature is equal to delta H of vaporization at the literature, right, at the standard value. So you have to, in the NIST webbook, you have to look up what temperature that value was taken at. Right? So make sure you get one where you know the temperature was taken at. And to correct it, we need this delta CP, delta T term. The delta CP part, that's just the heat capacity of the gas minus the heat capacity of the liquid. The delta T, that's the difference between the experimental temperature, the middle of your range, right, and the literature temperature, the one where this value was taken. And now what that allows you to do is create a literature value appropriate to your experimental temperature. And then you're going to put this all in a nice table, right, and compare your results for these two liquids to the results from the NIST webbook corrected for temperature appropriately. We also need to get rid of our sample. How do we do that? Right? You can't get this apart right now, right? If we want to change samples right now, this is under vacuum, right? And so don't forget that if you're under vacuum, right, then the atmosphere is pushing on this thing and it's holding the thing together, so you can't get it apart very easily. Besides, you don't want to like rip off the thermistor here and have a big inrush, okay? So instead, we gently vent it up. Gently vent it up to atmosphere. That will get all of this up to atmospheric pressure. And that way we can then take this apart, right? We can already take the Heatman mantle off of here, all right? So that cools down. This is open, well, that's hot. We're allowing that to cool down now as we vent to atmosphere. Right now it's being held together because we got the little clamp on there, little clip on there. Put this back up to atmosphere. Isn't sishing anymore, so it's not leaking, right? So that means both we can get the thermistor off of there, we can turn off the water, all right? And take off the little clip, and little clip. So, and then we're able to just twist that, boom, get it off of here. And then we've got the ethanol hand it in a little bit. We will dispose of that appropriately. Right, the ethanol can actually go down the sink. And heptane, of course, can't. That will have to go into a proper waste container, and heptane goes in with non-chlorinated solvents. You keep your polar solvents away from your non-polar solvents, right? So all of our organics go into one waste bin. Our aqueous waste go in a separate waste bin, right? This, since there's nothing else in for alcohol, it can go down the sink, right? But we don't want to throw the boiling chips down the sink, so let's just be careful. Right? And then that way we've got this all taken apart. We've just need to drain the condenser. Boom. And you will see, there it goes. Oh, it's a cool one on this one. See, it's got the little windy one there. It's really nice. Okay, so that way we can get rid of the water out of there. It's all going to be cleaned up. We leave the pump off. But the last thing that we want to do is vacuum systems like to be under vacuum. So what we'll do is after we dispose of the ethanol appropriately and have this cleaned out, don't leave the boiling chips in there, so we get it all cleaned out like that. Ethanol leaves it nice and clean by itself, so we don't have to wash it any more than that, right? Then we're going to hook this back up and pump it down. Vacuum systems like to be under vacuum. That'll help clean out the whole system and keep it clean. All right, so there you go. That is the determination of the enthalpy of vaporization, the equilibrium vapor pressure.